Welcome back to our podcast, and today we're going to be doing something a little different than normal. We're going to be talking about both noble gases and halogens, but instead of us each picking an element from each group, Anik is going to do the halogens, and I'm going to do the noble gases.
Yeah, so starting right away with halogen, we already we had like a brief overview of these before, so like just as a refresher, there are 6 halogens: fluorine, chlorine, bromine, iodine, astenine, and tennessine. The last 2 you don't really hear much about because they're radioactive, so I won't really be going over those as much as the first 4. But they are non-metallic. They're in group 17, so they're right next to noble gases, the second to last column or family in the periodic table. And if you don't remember, the name halogen comes from the Greek word halos, meaning salt, and I believe it's genin, meaning to generate, something like that. I don't know how to pronounce it because I don't know Greek. But, yeah, it literally means to make a salt. And none of the halogens can be found in their pure elemental form, primarily because they're found as salts or ions, because that's their most stable form in their ionic form. You will see them maybe bonded with each other, or like to each other. They are diatomic molecules, so a fluorine can be bonded to a fluorine in the form of fluorine gas. But you won't just see a singular fluorine atom just flying around. They make salts, and they're found salts as ions. Large saltwater bodies typically contain a significant number of halogen ion concentration. Oceans are comprised about 2% by weight of chlorine ion, and 9% of the Great Salt Lake in Utah, which sounds like a large amount, but I can do one better by telling you that the Dead Sea contains a shocking amount of 31.5% or 33.7% of a salt concentration. The Dead Sea is called the Dead Sea for a reason. Like 1/3% of its concentration is made up of salt. You can also find primarily that's like the chlorine ion, but you can also find bromine and iodine ions in the oceans or in brine wells, which are like salt mines. But they're typically found at significantly lower concentrations because they're just less common salts. Interestingly, too, I find they can also be found in organic compounds. So since they have 7 valence electrons out of the total of 8, they can easily share 1 unpaired electron with carbon and fill up the space similar to how like a hydrogen would fill it up, because they can only form single bonds, and it doesn't really affect the overall structure by causing like a bend shape or anything. However, because halogens are more electronegative than carbons, it does cause a slight polarity, which is where the carbon would be a little bit more positive charge, have a slight positive charge, and then the halogen would have a slight negative charge because the electron would be kind of pulled towards that halogen. And we will talk about electronegativity in more detail later as well. So,
Yep.
Yeah. But a common application for organic compounds of halogens is actually anesthesia. I can never say that word.
It's a fun word.
Anesthesia, you know what I'm talking about. So back in the day, the first anesthesia we used was a compound called ether. But that only worked like 80% of the time.
Well, that's helpful.
20% of the time, the patients would either wake up during the surgery, which is like one of my biggest fears.
Oh my gosh, that'd be terrible.
Yeah, or they wouldn't wake up at all.
Okay, so the first one is slightly better. You would assume it would be like, I don't know, they gave too much or they would die or something, but honestly, I could see where it would just be like certain people just can't handle it. So like,
I don't know entirely how it works. I just know that fact. But yeah, so we stopped using that compound And now we use in like terms of structure, a similar compound, but they contain halogens now. So compounds like halothane, enflurane, isoflurane, metoxyfluorane, and nitrous oxide, which is an outlier because it doesn't contain a halogen, but that's laughing gas, so it's not.
Yeah, it's not like quite
exactly the same.
Yeah.
But if you can pick out the sounds of those words, you should be able to see that they typically contain a lot of fluorine with like the fluorine part of it. And some of them have a few chlorine atoms in there as well, but fluorine's kind of the primary halogen. Fluorine itself, I find, is a very interesting element, so I'm just going to take some time and isolate fluorine and talk about that halogen specifically. So fluorine gas, F2, two fluorine atoms bonded together. It's actually a pretty toxic colorless gas, but a lot of halogen gases are pretty toxic. Chlorine gas is the famous one because it was used in World War I as gas warfare by the Germans. Wasn't the most effective weapon because it was carried by the breeze, and then sometimes it would blow the wrong way into their own troop. Yeah. Also, if you mix bleach together, a little PSA, don't do that. Don't mix bleach with other chemicals because it can actually make chlorine gas. And that can kill you. It like dissolves your lungs, which isn't fun, I've heard.
Yeah, I doubt that feels very good before you die.
Yeah, so don't do that. But back to fluorine. Fluorine is the most reactive element of like all 118 of them. So much so that it's actually really hard to store fluorine because it will react with glass and quartz and even make some metals go up in flames.
So the interesting stuff.
Yeah, the interesting stuff. That makes it really, really, really hard to store fluorine. And part of the reason why it is so reactive is because it is the most electronegative of all the atoms. And the electromagnetic scale is actually based off of fluorine since it's the most electronegative. And the reasons behind electronegativity is really hard to explain in detail, I feel like, without going into the really hard quantum chemistry aspects of it, which I feel could be its own podcast or episode in itself because it's so complicated. But the short answer to why it is the most electronegative is because of its size, electrons, and orbitals. So fluorine is the third smallest element, beaten only by the noble gases of neon and helium, which are noble gases, so
they don't bond. Doesn't count.
They don't, yeah. So in terms of elements that actually can bond and do stuff, it's the smallest one. And since it only has one open spot in its valence shell, it's one electron away from being perfectly stable and having the ideal optimal electron configuration. And because it's in the second row of the periodic table, it has only two orbital shells. As you go down the periodic table, you gain a shell, which increases like the atomic radius of it. But then as you go to the right of the periodic table, you add more protons, but the number of shells stays the same. So you're increasing the positive charge in the center of the nucleus, making all the electrons have this greater positive charge to be attracted to, which decreases the size. And because fluorine has pretty much, with the exception of the noble gases, but they're noble gases, so just omit those for the purpose of this, it has the largest amount of protons for its electron shells, if that makes any sense at all.
I think it might, but like another thing with what you said before, I don't know if this will help anyone understand it more, but like when you said there are more protons as you go to the right, you might also remember there are more electrons on the outside as you go to the right. So if you were thinking that, those things go together because you need more protons if you have more electrons to stay more stable. So if anyone was getting confused by hearing that, I don't know if they were, but I did for a second, so I wanted to share that.
Yeah.
Yeah.
it's complicated, and then there's like a bunch of weird things like subshells and just plain old shells and orbitals, and it's too complicated to explain in a podcast and this quickly. So, but yeah, basically, the primary thing that happens is that all the electrons are just really, really attracted to fluorine's nucleus, which causes it to be really small. And when fluorine will bond with another atom, because of how attractive the electrons are to fluorine's nucleus, even when it shares a covalent bond with another atom, that those electrons shared will still be favored towards the fluorine side of the molecule. Electronegativity is kind of the tendency of electrons to be attracted to an atom, I guess, is a decent definition of electronegativity. I don't know. We'll probably talk about it with Ashlyn as well. So
yeah, I didn't go into as much of a broad perspective with mine. Mine was more like, this is how it applies to the noble gases, because it's not the same. It's like, I didn't really go into like the whole thing, because that would be another podcast. So if you are watching this very far in the future, and we do have an electronegativity podcast, you should watch that and then resume this one, I think, maybe, or watch this one after, because that would probably be very helpful.
Yeah, the details of it are just, it's tricky. But anyways, electronegativity causes a lot of headaches when you apply fluorine and its electronegativity to acids and bases, because all halogens, when they are bonded to hydrogen, they make an acid. Like, I don't really include the last two of acidine and tennessine because they're radioactive, but iodine, bromine, and chlorine, when they're bonded with hydrogen, are like 3 of the 7 strong acids. So one would expect then that fluorine, being the same family, being a halogen and bonded with hydrogen, it would also be a really strong acid. But no, fluorine decided to be the problem child and decided that it was going to be a weak acid, which just really, really makes people angry when they're studying acids and bases and they're realizing that it's not a strong acid. And that, again, has to do with electronegativity. It means that the bond between hydrogen and fluorine is really, really strong. So it's called fluoric acid. A fluoric acid molecule is not really likely to give up the hydrogen, which is the definition of an acid. An acid donates a proton or a hydrogen ion, which are typically synonymously used as proton and hydrogen ion. So, yes, fluorine creates some frustration when it doesn't fit the trend. So that's pretty much all I have.
Yes, so now you know about the frustration of fluorine, but also how interesting it is. And so I did noble gases, but I didn't really have, like, I did pick an interesting noble gas, but don't expect it to be as interesting as fluorine, because fluorine is it's super, just like interesting and also annoying, and it's a cool element. Yeah. But I did noble gases, and there's 6 naturally occurring noble gases, and there's 7 altogether. And it's typically at the end, unless you have a super long one with the lanthanides and actinides added on, which it will then be before those. But in your typical periodic table, if you have the lanthanides and the actinides at the bottom, then the noble gases will be the last group. And they have helium, neon, argon, krypton, xenon, radon, and I believe it's pronounced oganesson. I don't know.
I think it's oganesson, but I'm not entirely
probably
sure.
Is. Okay, well, oganesson probably. So some like basic knowledge about noble gases. They have 8 valence electrons, so they don't need any more. Like, they have the full octet. They don't need to get one or lose one, which is why they don't bond, because they're just stable the way they are. They don't need to change to be stable. They're also very rare, and they can glow. So I think we talked about this in a past podcast, but basically what you do is you excite them in some way, like by charging them somehow or just somehow making them excited. And then they will release energy in the form of light, which is basically how you make neon lights. It's obviously more complicated than that, but that's sort of the basics. And then some just basic stuff about all of them. I did most of them except I did some basic facts on most of them. But argon was the first one discovered. And the Greek word argos, which you could probably guess means unreactive, because, it's a noble gas, and yeah. And then I just wanted to research radon a little bit, because if you've ever heard of radon testing or something, you know that it's a problem. Like, you can get radon in your basement because it's a very heavy gas, and it will, collect in your basement, and it can cause long-term health problems, like lung cancer, because if you breathe it in, it's actually a radioactive element, and if you know anything about Marie Curie, you know that radioactive elements are not good or healthy for you. And that's basically what I had on radon. And then I had a little bit on helium because I remember that a while ago, I don't know if it's still going on, but there was a helium shortage. And then someone asked me how you could have a helium shortage if it's an element. And I thought, well, it's going to just go up in the air, and then I researched it a little bit. And it's actually created multiple ways, but one of the ways it's created is when radioactive elements like uranium or thorium decay, because it's it's a very small element. And helium is the smallest element, so it makes sense that it would be created by radioactive decay. And it can also be found with natural gas, which is usually where you get it for your things like balloons and stuff. And what I also thought was interesting is if you've ever taken diving classes, you know that they want you to go down slowly, and especially they want you to come up slowly, even if you're in a pool, because they want you to get used to that. And that's because it's very easy to get nitrogen stuck in your blood or something, and it's very bad. And they take you to a decompression chamber and all that, or you can come up slowly, and that's what they want to teach you. But once you get lower than, I think it's 400 feet or 122 meters, the nitrogen in the air is actually replaced with helium, because the nitrogen can build up. And that's the same reason that they want you to come up slowly, and that's why they replace it with helium, so that bad things don't happen. And then I did do a little bit on electronegativity. Essentially, it's the greater the electronegativity, the more the element wants an electron. Like fluorine, it's electronegative because it wants an electron very badly. It has 7, it's tiny. And the easy way to tell if it's electronegative or electropositive is that if it's even, like with fluorine, it has 7 to be not charged in any way. It needs 7 to be neutral. And then if you add 1, it's negative. With electropositivity, it usually wants to give an electron away, which would make it become positive. I'm also going to talk a little bit about fluorine, just because it does have a little bit to do with xenon and a little bit with krypton. But xenon and krypton they can bond. Many of the noble gases can bond. They don't usually do it easily. But what you find with xenon is that if you take xenon and fluorine and you put it in a light bulb and you leave it outside, they will bond. And depending on how warm it is, like if you leave it out in Chicago, I think it takes an hour. But when they did it in Scotland, it took a week, because it needs more heat to bond. It's very easy to make, it's easier to make bond than most other noble gases, because for most other ones, even krypton, which is the second most bonding noble gas, you do need to heat it up to I want to say it was 600 degrees Kelvin or something like that. It was really hot.
Ooh, that's hot.
Yeah, it was hot. And you were all you need to do is this. I was that is it's not.
Yeah.
No.
For those of you who don't know what Kelvin is the absolute temperature, where 0 is absolute 0. There is absolutely no heat at all. And 0 degrees Celsius is the equivalent of 273 Kelvin. So 600 is really, really, really hot.
Yeah, it's just yeah, it's not super fun. I think it was. I want to say it was 600, but don't take my word for it. You might want to check that later. But yeah, that one can bond. Many of them can bond, but xenon is the easiest. And the Greek word xenos actually means stranger, which is where the name comes from. And the reason xenon can actually form with fluorine, even though fluorine is the most electronegative, which definitely helps it, is that xenon is the largest of the noble gases. And like we just talked about, protons are positive, electrons are negative, and neutrons are neutral. Neutrons and protons are in the nucleus, and then the electrons are outside. And the protons and the neutrons, well, mostly the protons, help the electrons kind of stay inside almost. But since it's the largest, the outside shell with the 8 electrons is held in the least because it's so far away from that positive charge. And so it's easiest to, which is kind of the reason why it's easiest to bond, because with most of them, like with helium, which is the smallest element, they're held in really, really close, and like they are not leaving. They're not going anywhere, which is why helium does not react, is because there is no way. None of those electrons are going to kind of inch out into another bond somehow. But with xenon, you can, since they're so far away, there are times when it will bond with fluorine at high temperatures because they're not held in as tightly as they would be with something like helium. Thank you for listening to our podcast, and join us next week where we will talk about some more interesting elements.